Hello and welcome to Algebra 1 with Miss Betsy. Today we're beginning a chapter on working with rational expressions. And in today's lecture we're going to learn how to simplify rational expressions, and we're going to see that that process is very similar to simplifying fractions by reducing them to lowest terms. But before we get started, could anyone tell me what the baby corn said to the mama corn? Well, he said, "Where's popcorn?" So if you're using my text, it's Algebra 1 for Christian Schools. It's published by Bob Jones University Press. I'm using the second edition. I'm on page 482, section 12.1, Simplifying Rational Expressions. And as I just said at the beginning, I alluded back to the fact that we had learned that a rational number was something that could be written in the form a over b, but b had to be different from 0. So b could not be equal to 0. So if we had 2/3, that's a rational number. If we have -7, that's a rational number. But if we have something that looks like 3 divided by 0, that's not a rational number, because we learned that division by 0 is not legitimate. So when you have something that looks like a fraction, we call this a ratio. If the denominator is 0, that's an undefined number. You cannot define it. What we're talking about today are rational expressions. And the difference in a rational expression and a rational number is this. We're going to say P1 divided by P2, P sub 2, is our pattern for a rational expression. In the numerator you have a polynomial. In the denominator you have a polynomial. The denominator, that second polynomial, nothing in there, same thing, it can't be equal to 0. So how are we going to be able to figure out if a polynomial is equal to 0? Well, sometimes you can tell just by looking at it. Sometimes you're going to have to factor. You might factor it by inspection. You might factor it by using the quadratic formula. So that's what we're going to be working on today. Let's go ahead and take two very basic examples of polynomials. And these are actually in your text. There are 6 of them on page 482. And we're going to go ahead and just look at these first 2 right now and just think about them. If we have x divided by x plus 2. Now, my definition where I said what a polynomial expression is, what a rational expression is, you have a polynomial in the numerator and a polynomial in the denominator. You say there is just an x there. Well, remember, polynomial can have just one term. We would call that a monomial. Technically, it's a polynomial. We have a binomial in the denominator here. Now, x can be any value in the world, but in order for this to be a rational expression, the denominator can't be equal to 0. So what happens, for example, if we say that x is equal to 0? Well, if x were equal to 0, we would have 0 divided by 0 plus 2. 0 over 2 is equal to 0. Good night. That's my daughter's cat. I don't know what his problem is. So you can use 0. There's a 0 in the denominator, but the whole value of the denominator, when you add that together, is just 2. So this is a rational expression if you have a value of 2 for 0. But what would happen if we substituted in and said, hey, let's see what we have. Let's give x a value of a -2. Substitute that and you have -2 divided by -2 plus 2, which then gives you a -2 divided by 0. Can you divide by 0? No, you cannot divide by 0. We learned the statement that said division by 0 is undefined. So, since we have determined a value, undefined, can't spell, undefined. Since we have determined a value for x, which is a -2, that causes us to that gives us a result of 0 in the denominator, we would say with this rational expression here, x divided by x plus 2, that x could not be equal to a -2. Remember our pattern for the rational expression said one polynomial divided by a second polynomial, but the second polynomial could not be equal to 0. So this second polynomial here, x plus 2, has a value of 0 if you give x a value of -2. Okay. This may be a little confusing and may be totally clear to you, but let's hang with me here. We're going to go through this new thought process here, and you'll see that it's really not all that difficult. This was the first rational expression we looked at. Let's look at the second rational expression that they give us. And this one is x minus 4 divided by 5. Seems really strange that you call 5 a polynomial. It is. It's a monomial, has only one term in it. It's degree 0. Remember, if you have any variable with an exponent of 0, anything to the 0 power is 1. So that's how they technically say that 5 is a polynomial. Now, rational expression, numerator, denominator. Denominator can never have a value of 0. Are there any limitations that we put on x here? No, there are no limitations at all, because 5 is always going to be 5. There's never any way that you can turn that into 0. You might say, well, what if x has a value of 4? Well, what happens? Substitute in a value of 4 for x, and you have 0 divided by 5. Is there anything wrong with that? Not at all. 0 divided by 5 has a value of 0. Only that you cannot divide by 0. However, you can divide 0 by any number, and you end up with that same value here of 0. Okay, now let's go ahead and look at example number 1 in your book. It's on page 483. And our question tells us, our instructions say, determine when the other 4 expressions that are on the previous page are undefined. Rachel, could you get rid of that cat, please? Our first expression here is x plus 6 x plus 6 divided by x minus 9. How are we going to figure out when we have a value? It's Georgie? Just put him outside, please. X minus 9. How are we going to figure out when that has a value of 0? Well, you very simply take that bottom binomial and see what happens. If you say that x minus 9 is equal to 0, go ahead and solve that equation for x by adding a 9 to both sides of the equation. So if x is equal to 9, we substitute a 9 in there. We're going to put a 0 in our denominator, which we're not allowed to have. So when it says determine the other 4 expressions, determine when the other 4 expressions are undefined, you would say that x plus 6 divided by x minus 9 is undefined when x equals 9. It's just a little bit of strange terminology that you're working on here. To determine when a rational expression is undefined, find the values of x, or find values of the variable that make that denominator have a value of 0. Okay? Let's go ahead and look at this next one. We have 3x squared plus 4x minus 5. (3x squared plus 4x minus 5 divided by x). We're going to take the bottom, take the denominator, and set it equal to 0. Nothing to solve here. This simply tells us that when x is 0, this whole rational expression is undefined. So you would say 3x squared plus 4x minus 5 divided by 5 is undefined when x is 0. See, this is an example of one I said sometimes you can just look at it and you know what the answer is. Well, you only have an x in the bottom, so if that x is ever 0, then this rational expression is going to be undefined. Okay, number 5. X plus 7 divided by x squared plus 3x minus 9. Now it's getting a little bit more interesting here. 5. X plus 7 divided by x squared plus 3x minus 9. How do we find the values for which this rational expression is undefined? You take the denominator and you make it equal to 0. X squared plus 3x minus 9 is equal to 0. And all of a sudden we have a factoring problem. Well, can we factor this by inspection? Are there two factors of negative 9? Two factors of 9, when you multiply them together you get a negative 9, but you get a positive 3? No, there aren't. So you cannot factor this by inspection. So what are you going to have to do to be able to factor this? Go back to your last chapter. Remember your quadratic formula that I said make sure you memorize? The value of x is equal to the opposite of b plus or minus the square root of b squared minus 4ac, all of that over 2a. Now how many of you, your eyes glazed over on that? And how many of you said, oh man, I'm so good. So glad I took the time to memorize my quadratic formula because you will use it. What are a, b, and c? These are the coefficients of a quadratic expression. Ax squared plus bx plus c is equal to 0. This is a quadratic second degree equation. The a is the coefficient of the square term, the b is the coefficient of the first degree term, and the c is the constant. So let's just go ahead and do our substitution. We have x is equal to the opposite of 3 plus or minus the square root of 3 squared minus 4 times 1 times a negative 9. All of this divided by 2a. And I should go ahead and put in 2 times 1. Now, if you're going ahead and looking at this, you see that we've got a very real problem. Because we are going to have some interesting values here. X is equal to negative 3 plus or minus the square root of, we have 9 minus a negative 36, which is 9 plus 36, plus or minus the square root of 45. All of this divided by 2. Now, what are you going to have to do? You're going to have to simplify this, because that square root of 45 doesn't work, does it? Remember, if you have any perfect squares, you have to be able to pull those out. There are some real disadvantages to having limited blackboard space here, whiteboard. We go ahead and pull the problem up here and finish it. How are we going to simplify the square root of 45? We have x is equal to negative 3 plus or minus the square root of 9 times 5. We have that perfect square of 9 that we can pull out. All of this divided by 2. X is equal to the opposite of 3 plus or minus 3 times the square root of 5. All of that divided by 2. You look in your book, x plus 7 divided by x squared plus 3x minus 9 is undefined when x is equal to negative 3 plus or minus 3 times the square root of 5 divided by 2. How do you know when a rational expression is undefined? You know a rational expression is undefined when you have taken that denominator, set it equal to 0, and solved for the values of x that will give you a 0 denominator, or a 0 result to this quadratic expression here. Okay, there's no way that we are going to be able to sit there and say x squared plus 3x minus 9 factors into this. So this is why you have to know the quadratic formula. Now let's go ahead and look at our very last rational expression in example number 1. And see how we can determine when it's undefined. We have 2x squared plus 3x plus 6, 2x squared plus 3x plus 6, all of that divided by another polynomial, which is x squared minus 8x plus 7. We have to determine what values of x substituted in here will give us a denominator of 0, because when we have to have that limitation because our rational expression is undefined anytime we have a denominator of 0. So you take this denominator, x squared minus 8x plus 7, and you set that equal to 0. Now you look at this, the very first thing you want to say is, can you factor it visually by inspection? You go, yes, I do not have to use this quadratic formula. X minus 7 times x minus 1 is how this factors. Negative 7 times the negative 1 is positive 7. Negative 7 plus a negative 1 gives us a negative 8. So we now have our factored form. So this would be x minus 7 equals 0, or x minus 1 equals 0. So this rational expression is undefined for two values. When x is equal to a positive 7, or when x is equal to a positive 1. So you see that we're pulling all sorts of concepts and all sorts of information together to come up with the values of x that cause this rational expression to be undefined. Okay? Now the second part of simplifying rational expressions comes to the comparison that we have with reducing fractions to lowest terms. Remember, let's say that you had 12/15ths. And I said, okay, 12/15ths is correct, but it's not reduced to lowest terms. So if you give me an unreduced fraction in the answer, I'm going to take half the credit off because you haven't reduced this to lowest terms. And we learned that you could say that 12 in factored form was 3 times 4, and 15 in factored form was 3 times 5. You could cancel common factors, and you would see that that doesn't look right. 3 times 4 is 12. It's sort of the middle of the night, so I have to be careful here. 12/5 times 3 times, yeah. Sorry for that momentary brain freeze there. The 4/5 is the factored form of 12/15ths, or the reduced form of 12/15ths. And we're going to go ahead and use this similar procedure, because we learned that if you had a fraction, a over b, that could be written as a times c over b times c. It was this pattern right here is what allowed us to write the fraction 12/15ths as a times c over b times c. We canceled out the c's. That's where we canceled out these values of 3. Right here. And we're going to be doing that same thing with simplifying polynomials. Our example here says 4a squared divided by 8a. This is a review of what we've done in the past with canceling, with reducing monomial rational expressions. What factors do we have in common? You have a factor of 4 in common, you have a factor of a in common. That's actually, I think, supposed to be a cube. That's supposed to be 4a cubed. Look at how I can write this. 4 times a squared divided by 4 times 2 times a. What common factors do you see here that you can reduce? That you can cancel? You can cancel the 4's. You can cancel the a's, and you have a squared divided by 2 is the reduced form of this rational expression. Okay, let's go ahead and look at another example that is, yet again, some review for you, but it doesn't hurt to ease into what we're doing. It says simplify 180 m cubed n squared divided by 27 m n. Now I'm going to go ahead and write out factorization here and say that this would be, let's see what I want to put, 9 times 20 times m squared times n, 9 times 3 times m times n. I'm not going into how I came up with this because this right here is review of what we've done many times in the past. But 9 times 20 is 180, 9 times 3 is 27, m cubed, n squared. And I'm going to illustrate how we're canceling common factors. 9 divided by 9 is 1, m divided by m is 1, and divided by n is 1. Now there are no more common factors, nothing else that we can reduce. So we end up with 20m squared n divided by 3 is the simplified form of this rational expression right here. Let's look at our book. 20m squared n divided by 3. And you could use exponent rules, m cubed divided by m is m squared divided by n is n. But whatever method you use, you end up with the simplified form of this expression being 20m squared n divided by 3. Now our final example in our text is where we're really getting into simplifying, well, I'm going to do 2 more examples, where we're simplifying rational expressions, where we have polynomials, true polynomials, not just a monomial in the numerator and the denominator. This says simplified 4x squared plus 4x minus 48 divided by x minus 3. Okay, now this is a good example of what we're really talking about when we're simplifying rational expressions. Remember, we have factors. We use the factoring by inspection to get a binomial times a binomial gave us a trinomial. This would be, we can think of this in parentheses there as a factor. So we're hoping that there's going to be a factor of x minus 3, but I don't see any x minus 3s up in that numerator. Do you? No. So what do we have to do first? Well, the first thing that you do when you're factoring a trinomial is you look for a common monomial factor, which there is. It's a factor of 4. 4 times x squared plus x minus 12 divided by x minus 3. Now, if you look at this, this is x squared plus x minus 12. That's something that you can very easily factor. And just as a hint, in Algebra 1, usually if you've got a binomial in your denominator, your numerator is going to factor so that that will at least cancel. It doesn't always happen, but that's a good hint to push you in the right direction. And sure enough, that's what we have going on here. If we do x plus 4 times x minus 3, we have factored our trinomial here, haven't we? Foil it back. X squared minus 3x plus 4x is a positive x. Plus 4 times a negative 3 is negative 12. Now, do we have common factors? Yes, we do, because we have a binomial factor of x minus 3 in the numerator, and we have that same factor of x minus 3 in the denominator. What do we have left? We have 4 times the quantity x plus 4. And we don't want to do 4x plus 16 because we want to leave this in factored form. So, 4 times the quantity x plus 4 is the simplified form of 4x squared plus 4x minus 48, all of that divided by x minus 3. Never would have thought that when you first started learning how to factor. But this is exactly what we use our ability to factor polynomials for, so we can come up with a reduced form of a rational expression. So let's go ahead and do our final example for this section. And let me get my book here. We have x squared minus 4. All of this divided by x squared plus 4x plus 4. There's nothing here that we can factor. You can't, and do not fall into the trap. You cannot factor x squareds. You can't cancel those x squareds. You can only cancel common factors. Let me use this as your reminder over here. 3 times 2 divided by 3 times 7 is equal to 2/7, not 2/2, is equal to 2/7. 3 plus 2 divided by 3 is not equal to 2, is it? You cannot cancel terms. You can only cancel common factors, so you cannot cancel terms of a polynomial that has to be in factored form. So let's look at this numerator. X squared minus 2, you need to recognize that as the difference of two squares. That becomes x plus 2 times x minus 2. Our denominator, this is actually a perfect square trinomial, but I'm going to go ahead and, so it's x plus 2, the quantity squared, but I'm going to write it out this way, x plus 2 times x plus 2. Have to be able to factor. Can't do it any other way than say you've got to be able to factor. Now, we have two binomial factors in common. So the simplified form of this rational expression is x minus 2 divided by x plus 2. So you can see that you've got a lot going on. You have to be able to factor, then you have to recognize what common factors you have that you can cancel, and that's how you simplify rational expressions. We'll continue on with this next time.